Thank you.
Ladies and gentlemen, Dr. Belmont.
Thank you. That's nice to come back to. All right, so I've also got a few announcements, so I suppose that's first announcement, your homework is due on Wednesday. Make sure you have it done. Second announcement, I sent you a little link, or I sent you a little announcement right before this class about this little sort of new 1-credit modules the BME department is offering. You should really sign up for those, or at least take a good look at them or vote on them. The link, it turns out, that I had sent you the first time doesn't work, but the one on Canvas now does. I apologize for that. They sent me the wrong one. I sent you the wrong one. It happens. But if you are interested in that, go check it out on Canvas. And then finally, the third announcement I'm going to be making is the last week's lecture, last Wednesday's lecture is on YouTube. You'll have a link to that. Watch it at your own pace. Watch it however you like. You will be responsible for knowing that stuff, so definitely watch it. To that end, I will also, someone had suggested I share all the videos I've taken in this class before the final, so I will do that. After the final class, I'll just start uploading every single one so that you can use them to study and just watch me. Continuing our survey of biomedical engineering, we're going to again keep to, oh goodness. You know, this thing just likes to break every now and then. Okay, we're going to keep using Will Durant's Fallen Leaves as our sort of outline. Today we're going to be talking about our souls, our gods, religion, and morality. So we're going to be talking about some cool stuff. Also cool stuff, and just keeping with the tradition I've now established of introducing you to some of my intellectual heroes. Here's a fellow by the name of David Foster Wallace. He's another one of my sort of just heroes. He's written many, many, many books, most famously Infinite Jest, which is considered one of the greatest postmodern novels ever written. So if you got about 60 hours to spend reading a book, check that one out. It's really great. And we're actually going to just use a bunch of quotes from his commencement speech. I think it's really good. Actually, if you have a chance, for our 200th bicentennial here at Michigan, we have a commencement speaker by the name of Jesmyn Ward, who's another one of my favorite authors. She's giving that December 17th or something. If you have a chance to go to winter commencement, I would really recommend it. It's going to be great. But to David Foster Wallace, he begins his commencement. There are these two fish swimming along, and they happen to meet an older fish swimming the other way who nods at them and says, "Morning, boys, how's the water?" The two young fish swim on for a bit, and then eventually one of them looks over at the other and goes, "What the hell is water?" Has anyone ever heard this before? Has anyone ever heard the "this is water" speech? Yes. Okay. Well, the point of the fish story is merely that the most obvious important realities are often the ones that are the hardest to see and talk about. Stated as an English sentence, of course, this is just a banal platitude, but the fact is that the day-to-day trenches of adult existence, which you've now entered, banal platitudes can have a life or death importance, or so I wish to suggest to you on this dry and lovely morning. To that end, I suggest we start talking about our souls. And biomedical engineering actually offers us one really cool way to peer inwardly. And by that, we can kind of peer inwardly like this. Does anyone know what this is an image of or from? It's an X-ray. What kind of X-ray? Yeah. It's an X-ray CT scan, an X-ray computer tomography scan. That's CT. When we talk about CT, this is usually the one we're talking about. The images kind of look like that. Okay, so the first part of that is going to be somewhat important. What the heck is an X-ray? Well, an X-ray in its basis form is a form of electromagnetic radiation. Just like the visible light around you, just like radio waves, the thing that cooks your turkey potentially in the microwave, all of these are electromagnetic forms of radiation. X-rays have wavelengths from about 0.1 to about 10 nanometers. If we then go ahead and look at the scales of life on which we are duly familiar from earlier in the course, that puts us right around the molecule stage. You know, a little bit smaller than a ribosome, but pretty much bigger than our amino acids. Right in between there are the size of X-rays. X-rays also correspond, if you don't like thinking about them in wavelengths, you can think about them in frequency components. And they go from about 30 petahertz to 30 exahertz. You may not have heard those before. suffice it to say, it's quite large. X-rays were also discovered, and because we in this class now appreciate that discovery and the credit for scientific notions and inventions and all sorts of things is always a little more wishy-washy than the story that gets told. It was discovered around 1895 by a fellow by the name of Wilhelm Röntgen. And you'll often see X-rays called Röntgen rays for that name, or for that reason, who even gave us the first medical X-ray on December 22nd, 1895. And it was actually of his wife's hand. And this is the very first medical X-ray. I think that's pretty cool. And I think it's so cool, I blew it up. Put it right over there. X-rays can do essentially two things when they interact with a material. They can either be absorbed or they can be scattered. When we talk about an X-ray being absorbed, what we mean is the X-ray's energy is diffused, is taken up by a material. And that, it turns out, is a function of the atomic number, such that if you have a higher atomic number for an atom, it's more likely to be absorbed. If it has a lower atomic number, it's less likely to be absorbed. To say again, absorption is itself a function of the atomic numbers, where the greater the number, the greater the absorption. Scattering, on the other hand, is an inelastic interaction of the X-ray photon, because again, when we talk about electromagnetic radiation, we're talking about photons. We're talking about little packets of quantas of radiation. Interact with the outer shell of an atom, the electrons of the outer shell. And then it scatters, and it kind of bounces off and goes this way and that. So then I pose to you, why do we see bones and not, say, the fleshy bits? When we took that picture of that CT, we mostly saw the fellow's, actually I think it was a lady's skeleton. Why do we see that?
Your flesh is mostly water and maybe carbon, so that has relatively low atomic numbers, whereas your bones are made of a lot of calcium, which will have a higher atomic number, so you'll absorb it.
Yeah, fantastic reasoning. We are, at base, salty water. That's mostly what we comprise. Our bones, however, have calcium. Since water's largest atomic number is, 8 for oxygen? You chemists in the room can correct me. Is it 6? Is it 8? Something like that.
8.
Oh, right. Calcium has, I think, 20? Is that 20? 20?
21.
21? Okay. Some people got it memorized. I just look it up on the table. So yeah, the higher the atomic number, the more likely we are to see it. So why do we see that ring? It's metal, and metal has high atomic numbers. Very good. So yeah, that's what X-rays are doing. They're getting absorbed, and we're seeing the absorption. That basically means all the white part is when an X-ray went all the way through. When it hits something, it gets absorbed and we don't see it. It's black. In modern medical imagery, we just reverse that because it's easier to see white stuff than it is black stuff. It's the only reason. Okay, so how do we get to X-ray computed tomography? What the heck does computed tomography even mean? Well, first we need to know what tomography means. And tomography, in the sense we tend to use it in medical imagery, means building up a three-dimensional structure, a volume, from two-dimensional slices or sections. And actually stated more broadly, more generally, it's the process of building up higher dimensional images or forms or volumes, however you want to think of them, building up higher dimensional things using lower dimensional things. So in fact, the first X-ray tomography machines were one-dimensional. You know, the data was one-dimensional. It was a little pin beam, a little slice of light. And we were able to build up three-dimensional structures from that. So if you've ever watched any sort of medical show, you've probably seen little slices like that. Each one of these little slices is a two-dimensional, thing. And you stack them all on top of each other, and you can build up a three-dimensional structure. So that's what's happening here. We've taken slice, 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 and we just stack them one on top of the other, and we build ourselves a skeleton. And the way this actually gets done in general practice is by using not only a big old machine, which is just a big circular X-ray that shoots X-rays and moves around, but we have to use some digital image processing, also known, and digital geometry processing. We need to kind of know things about geometry in digital space to convert the X-ray images that we get, these X-ray scans, these two-dimensional objects, into the three-dimensional volumes that we care about. Now, when you talk about a volumetric pixel, a pixel that doesn't just take up a 2D grid, but actually has a thickness to it, that's known as a voxel. We deal with a lot of voxels in medical imagery. Actually, this might be a good thing to know. Most medical imagery, I didn't write this down, but you should, are saved in a standardized format known as a DICOM. You can all look this up, but I believe it's called, let's see, Digital Images and Communications of Medicine, something like that. And this is a standard format. So if you ever see a DICOM, it might be of a CT. And a DICOM is just really a fancy way of stacking up JPEGs, little slices of pictures, one on top of the other. It's giving JPEGs thickness and a position in space. You should be aware that they exist. Okay, has anyone ever seen the inside of one of these things? Kind of look like that. They are fairly complicated. Right up here, we've got ourselves an X-ray generator. It shoots down an X-ray. In this case, a beam, a fan of X-rays that are all themselves received by a receiver. And we spin that around over and over and over in a corkscrew pattern, and that builds up each of the slices that we care about. Now, the math involved in making that happen is a little beyond the scope of this class, so we're going to kind of step beyond it. But I figure I may as well show you what it looks like. There's also two other things that we're not going to mention. Again, this is a necessarily superficial view of something like X-ray computed tomography. But there's two other kinds of computed tomography that you should know. Even though we tend to talk about CTs as being X-ray CTs, that's sort of the modern parlance, there's two other main important ones. There's positron emission tomography, where gamma rays interact with a substance and emit a positron. And this is usually for observing metabolic processes, usually via something called a tracer. So you inject a little bit of dye into somebody, shoot them with some gamma rays, they emit some positrons, and you recognize that in three-dimensional space. That's known as positron emission tomography. And then there's the larger, oh yes?
Is that something that would be used to like monitor like cancer? Or like
I mean, yep. PET has been used for to monitor cancer, yeah. You want to use it for your project?
No. No, I had skin cancer when I was little.
I'm sorry to hear that.
No, I'm like fine.
Oh.
But I've had MRIs like every 6 months, so I'm like kind of curious.
Well, so this isn't an MRI. This is a PET scan. We'll get to MRIs though. They're actually totally different mechanisms. So this was shooting X-rays into you. What an MRI does is jazz you full of magnetism, and then sort of pokes you and dips all your electron, your dipoles in one direction, and then it takes a little image. We'll get to that. It'll make sense in about 20 minutes. Actually, I think it's right after this, so never mind. It'll make sense in like 2 minutes. But yes, you are right. The other one, it's a sort of a bigger mouthful, is single photon emission computed tomography. This is, I believe, sort of the most recent one of what we're talking about. It's also called SPECT. And this really detects biological functions, so the flowing of blood, for instance. Not necessarily something metabolic where there's chemical reactions going on, but if you start seeing like the movement of air and fluids and interstitial spaces, things like that, that's really where you're going to be using SPECT. Yes?
So the first one is like you ingest some sort of tracer, which is then viewed, right? And then the second one, would that be like basically inject some sort of tracer into like your blood, which is then viewed?
Yep, you've got it entirely right. And I should mention, single photon emission computed tomography is the highest resolution of the ones we have. But it does require the use of a tracer, which computed tomography, just regular old X-rays, don't necessarily require. So as we kind of mentioned, this big old machine gives us a pretty three-dimensional picture. Is there any, yes? Any questions about this?
Well, not about this, but for the single photon, that one. If you can detect like the movement of blood, for example, but you also, let's say you had like a wire through an artery or something, to be able to detect the movement of that.
Yeah. Yeah, you don't even need to use specs for that. You can use that for, that's what they do in what's called angiography. So angiography is x-rays of your blood vessels and trying to see the movement of blood within your blood vessels. And you often will use or track your cannulation wire doing that. Yep. In fact, you can't do that using the following technique: magnetic resonance imaging, which you will be excused if you think that this tube looks essentially like the other tube, because it does. They look a lot alike, and if you didn't kind of know the difference, you wouldn't know that you really don't want to have a pacemaker near one of these. The reason you don't want a pacemaker near one of these is you're actually going to generate, with magnetic resonance imaging, a very high strength magnetic field, about 100,000 times greater than the Earth's magnetic field, actually up to 1,000,000 times. The units of magnetism, does anyone know what that is?
Tesla.
Tesla. Very good. Yeah, the units of magnetism is Tesla. The Earth's magnetic field is about 1.0 times 10 to the negative fifth Tesla. And a standard, so that's the Earth, that's your poles on the Earth. And your standard MRI magnet, that'll usually be about 1.5 to about 3 Tesla. It goes all the way clinically to about 7, or experimentally to 7 and 15 Tesla, but you won't see that in practice. In a hospital, you'll see about 1.5 to 3. So very, very powerful. You don't want your pacemaker anywhere near that. And the reason we do that is what we're trying to do is align all the dipoles in your body, and especially the water molecule dipoles, in one direction. We want all of, and a dipole, in case you didn't know it, is a distribution of charge, an unequal distribution of charge. So you got a positive and a negative on one side. Water molecules are very dipole-licious. They're very polar. And so if you subject them to a very large magnetic field, you can make them paramagnetic. You can force them in one direction. Now, the actual resonance of magnetic resonance imaging is a little complicated to talk about, so we're going to step back and talk about something a little simpler. We're actually going to talk about the relaxation. But what we do is, so we've got all of our molecules aligned in one direction. Then what we're going to do is we're going to knock them over with another magnetic field. So we've got one magnetic field going in one direction, and we're going to subject it to a very small pulse in an orthogonal direction, typically, say 90 degrees. And then we're going to watch the dipoles decay back towards their original state, back towards the driving magnetic field. So we subject them to a tiny pulse, which knocks them over, and then they're going to be righted back towards equilibrium. This is a thing known as relaxation. There's two kinds of relaxation, neither of which you get to have in this class, because we just go at a clip, you know, which we'll talk about here in a moment. Then finally, for the imaging part of this, we do this over and over and over and over again until we basically looked at all the molecules, or a lot of molecules, within the magnetic field. And different materials decay at different rates and in different ways. So recall that I had said that there are two kinds of relaxation. Not only do they decay at different rates for different materials, but they actually do it in kind of distinct ways. And this can help us in our imaging. Any questions on this? Yeah?
You feel your molecules being written?
You cannot. Maybe you can, but I don't suspect you could. It's down at the molecular level. It's like saying, can you feel, you can't really even feel your blood coursing through your body, right? And it's moving a lot. You know, it's shooting out of your heart at about 2 meters per second. You don't feel that. So, yeah.
So
Average velocity is 1 meter per second, but your peak is 2 meters. Yeah.
So might they like inject some kind of material to watch, like when you get an MRI?
Sometimes, yeah. Actually, you're the expert here. What do they do with MRIs?
Well, I don't know. I was 5. Right?
You weren't taking copious notes for your
So,
future
like,
biomedical
yeah,
engineering
no.
career.
For all I know, I could have had any of those things. I just know that they gave me a weird shot, and my dad was like, "They're gonna give you this thing. It's to make you blow into the camera." It's like, okay.
So you are right. They do tend to give you a shot of a dye, usually gallidium, and that's meant to perfuse into your tissues and watch certain things. Yeah, you are right. Again, that's a little beyond the scope of what we're going to talk about here. If you've got any questions, Ashley's the person to ask. To kind of give you a sense of what that looks like, we'll take a look at it here. If we observe right here, we had everything going in one direction. We subjected it to a 90-degree pulse. Well, now and it's starting to kind of diffuse apart. We're going to subject it to another, a 180-degree pulse, and now they're going to come back together. And that's going to give us an echo, where they all come back together. This is known as spin echo imaging. We'll watch it again. See, we've got everything going in one direction. We've already aligned it, and now we're going to hit it with that orthogonal pulse that I told you about. It's going to knock our dipole over, and now just given the uneven distribution of the magnetic field, they're going to start to spread apart. We're going to flip it again by 180 degrees. We're going to hit it for a little bit longer, and then we're going to watch them come back together. As all the dipoles come back together, they're going to have a little echo, and we pick up that echo, that little small coming back together of dipoles. Give you one more chance to kind of see that. Again, we've knocked it over, and it's going to fan out. So what we're not showing here is that this is actually also tipping back upwards. I'm just showing it kind of spreading out. But because there's a magnetic field still pushing it this way, it's also, in addition to just fanning back together, it's also tipping back upwards. Another way of looking at that, or here, I suppose these are things I should have told you about. The first kind, when it's decaying back up, just as I had mentioned, that's known as a spin lattice decay. And that's the relaxation, that's the going back to the original state in the Z component. And this is characterized by a time constant called T1. Now when you talk about MRIs, you're going to hear T1 and T2 until you don't want to hear it. That's kind of the long and short of it. T1, this spin lattice relaxation, really highlights things like fat and the little shot that Ashley had gotten, gadolinium. Gadolinium in high doses can be dangerous, or some people can be allergic to it. But for the amounts that we give you in MRI, typically it's fine, as long as you're not drinking the stuff, in between MRI sessions. The other kind, the sort of fanning out, this is known as spin-spin decay. This is the transverse relaxation, when everything kind of just eases up, where it doesn't want to be all in one direction. And this is characterized by a time constant called T2. And this highlights things like water, tumors, inflammation. Now again, you've got spin lattice decay, or spin lattice relaxation, that's T1, and you got spin-spin decay, that's T2. Yes?
So if the MRI can it shows when there's the echo and they all meet together, that's what it reads. Why do you have to flip it over? So when they still connect the original way?
So no, right now it's kind of showing that it might do that because it's kind of going naturally that way, but there's no reason why it needs to go out uniformly like this. This is just a simple demonstration. You get things known as coherence and decoherence. In order to deal with that, we kind of flip it back over so that it comes back together. Good question. Yeah, that's one of the problems with doing it kind of simply like this. Another way of looking at this is, imagine you've got yourself a dipole that's going in one direction, you flip it over, and you can see it decay back upward. And this is sort of what it looks like with respect to time and these two magnetic positions. So you can see one decays, one goes that way. We can characterize our T1 and our T2 constants like this. This is not necessarily something that you need to be able to do. The math is actually somewhat involved. But as long as you understand the basic mechanisms of what's going on, what we're doing in an MRI is just applying a real powerful magnetic field to get images that look like this, or to cause a phenomenon that looks like this. We actually don't see this. Do you actually know what we see in an MRI? It actually looks like that. This is what the data from an MRI looks like. Does anyone know what that is? Yeah, your doctors don't either. That's actually your head. It's basically You know, there's your eyes right around there. There's your nose. Actually, let's see. Your nose would probably be right around here. This is a thing known as K-space. Because it turns out we can't actually measure all that decay because it's happening at the molecular level. It's really, really small. We're talking about dipoles and atoms all spinning in certain little directions. But what we have to actually measure is the frequency of those spin echoes. And this is the frequency domain in magnetic resonance imaging. That's what K-space is. And so what this actually represents, we kind of look at it, this is Kx, this is Ky. Then a point like this over here is representing kind of high frequency horizontal bands of black and white. Somewhere over here, we've got sort of diagonal bands of black and white that are at about the same frequency. If we start to get closer to the center, to the origin point, we get low frequencies. Here you've got a big white pulse, then you got a black pulse, and you have another big white pulse and a black pulse. So that's our low frequencies. Here you can see somewhat lower frequency diagonal that's now going in a slightly different direction. Here you've got a lower frequency still, but now is going entirely horizontally. And here you've got that high frequency going in a different direction. So here we've got our horizontal lines, here we've got vertical lines. All of this then needs to be converted through, again, fancy pants mathematics known as the Fourier transform. Fourier transform, I've heard it both ways. Fourier transform to convert this from two-dimensional frequency domain to the spatial domain. And as if you kind of now look at this image, knowing what it is, you can see, something like this right here, where you've got an eye that meets sort of the eye cavity. Well, you might see a low frequency pulse, something like that. A nice vertical line right there that would get highlighted by a point like this. Here you can see some of these diagonals. That might occur somewhere right here, and it might occur here and here. All of these combine together to give us this image here. Any questions on that? Okay, that's magnetic resonance imaging. If you're actually interested in it, we have a PhD defense coming up. A lady by the name of Kathleen Panagas. I knew her as Kathleen Rapella. She recently got married. And she's actually going to talk about ways of improving MRI sample collection. Because that's all MRI people do. They just think of better ways of doing it. I'm actually, unfortunately, I'm looking at the time here. Let's see. If we've got time at the end of class, I will go over ultrasound imaging. This is my thesis. Actually, you know what? What the heck? We're doing it. We're doing it. Can I go back to what?
The MRI.
What do you want to know about the MRI? Ah, this, yeah. Definitely, and if you go, I'll be there, but just show up. It's great. You all should start to see what sort of cutting edge, bleeding edge researchers are doing. This is what Michigan is great at, and this is, a brand new PhD. So, assuming she gets it. But she will. All right, so now what we're going to do is a little bit of derivation. Everyone's favorite thing. And the thing we're going to talk about with ultrasound is the derivation of the wave equation. So you've got yourself a volume V right over here. You've got yourself V with dimensions X, Y, and Z. We're going to introduce the idea of, imagine we had this volume V, we'll call that V1, and we applied a pressure. We have a P1, and we've got now a P2, call that V2. We're going to introduce a concept here known as the bulk modulus. That's KB is equal to P1 minus P2 all over V1 minus V2 divided by V1. Another way of seeing this is basically saying delta P over delta V. And V here, I'm going to put a little crossbar just so it represents volume. As this is my thesis topic, you can pretty much guarantee you're going to have a homework assignment on this. So, get familiar with it. All right, so now let's imagine we applied a force F on something like this. What this force F is going to end up doing is it's going to stretch this material by an amount x, or by an amount delta x, so you'll have x plus delta x, and it's actually going to move it from a position to u and delta u. So we've, in addition to stretching the material, we've also moved the material. So there's elastic and mass transport phenomenon going on. The basis of this, you can imagine, F delta x. So if we do maximum displacement, we do the energy required, we'll do an energy balance. I suppose I should have said that. Let's figure out the energy balance. What's going on? We've got delta F, or not delta F, F times delta X, which is the energy required to sort of stretch that material, is going to be equal to the bulk modulus times the area times that delta U. So that we can say F is actually equal to KBA times delta U over delta X. And I'm actually going to start to represent this as a partial differential. I know you haven't got there, so I'm going to write where you normally see a D, I'm going to use the del. Don't freak out, it's the same thing, but because this actually has y and z components, we're going to do it in a partial.
What was the A?
Oh, my apologies, that's your area. The area, the cross-sectional area. So that would be, if we're looking at, on the x-plane, the A is just the cross-sectional area, y times z. All right, so that's going to make it, let's see, that'll be KB times A del U del X. Now, what is force equal again? You know it's not MA. What is it really? Oh, I told you about this earlier in the year. What is it in the... It's not times the derivative of the velocity. That's all A is. It is the derivative of momentum. That's what P is. It will do you a lot of good to think of Newton's second law in this way. Force is equal to the derivative of momentum, which in this case is the derivative of mass times velocity over dt. And the reason we represent it this way is there's actually a mass transfer. So you can't just imagine mass isn't changing, because it is. So you can imagine that delta F, the force accelerates a mass, delta M, accelerates mass, and mass here is actually rho A times delta X, where rho is your density, A is your cross-sectional area, so that delta F ends up equaling rho A delta X del square U del T squared. Now again, I'm saying del. That's the same thing as D in your derivatives. I'm using del because it's a little more accurate here. Since we could be going in any of these dimensions, we're doing it partially in the X dimension. No need to freak out. The math is essentially the same. So now what we can do, now that we've got a measure of, oops, I got that one wrong. My apologies. There we go. That should have been deltas. Someone should have been paying attention to me a little better. We can now combine these two functions. So that delta F, which is equal to rho A delta X del square U del T squared, is equal to KB times A del U del X, del U del X. So I have that right. Let's see. U is the displacement. Oh, what the heck did I do wrong here? Oh yeah, My apologies. Ah, goodness. I apologize, everyone. I got this portion of it a little bit wrong. This was, in fact, F. I don't know why anyone would think it wasn't. I apologize. I'm still getting better at this derivation thing. We want to differentiate this so that we actually figure out what F does with respect to X. So we'll do delta F over del X, and this will actually give us our KB A del square U del X squared. My apologies, everyone. My apologies. I'll include a better derivation of this online as a result. You should still follow what's going on here. All right, so now we've got ourselves a couple nice things that can be done. We can get rid of this A. Oh yeah, and this should actually have a delta X as well. My apologies, because we would have moved that over to this. I am just, you know, the math looks so much nicer in my head. You know, you got to put it up on the board. It's much harder. We can get rid of the A. We can get rid of the X. This leaves us with a saying of rho del square U del T squared is equal to KB del square U del X squared. We can then say that del U, let's see, I'm going to flip, here, we'll put it all on this side. Rho KB del square U del X T, or del T squared is equal to del U, or del square U, del X squared. We can actually call this something. This is known as C. This is the speed of sound. Actually, C is equal to the square root of KB over rho. This is the speed of sound. So that what we finally get is the wave equation. This describes just about every wave you'll ever see, ever in your entire life, including each and every ultrasound pulse that's ever been had, which is del square U over del X squared equals 1 over C squared del square U del T squared. This has both an accelerated term and an elastic term. So a mass transport term and an inertial term. I will leave it to the interested reader to derive that. Or to find a solution to that. If you're familiar with your Euler functions, it would help. Hopefully you are. Everyone's got their Euler functions memorized, yeah? All right. One thing I want to, so another quote from David Foster Wallace. Again, I'm just going to subject you. He was what was called a maximalist. So if he uses a bunch of words, there's a reason for it. So we will read. Here is just one example of the total wrongness of something I tend to be automatically sure of, which to me includes ultrasound and its derivation. Everything in my own immediate experience supports my deep belief that I am the absolute center of the universe, the realest, most vivid, and important person in existence. We rarely think about this sort of natural, basic self-centeredness because it's so socially repulsive. But it's pretty much the same for all of us. It's our default setting, hardwired into our brains, or our boards. Yeah, our boards at birth. Think about it. There is no experience you've had that you are not the absolute center of, even the one you're experiencing right now. The world as you experience it is there in front of you, or behind you, to the left or right of you, on your TV, on your monitor, and so on. Other people's thoughts and feelings have to be communicated to you somehow, but your own are so immediate, real, and urgent. After the break, we're going to come back and talk about people's feelings on God. So take a 5-ish minute break, or actually about a 3-minute break. If you need to sign up, go see Dr. S or Dr. C in the background. Man, I should have done that better. What's that? Not on Wednesday, on Tuesday. It should be 12:30 to 1:30. If you can't make that, send me an email and we can set up another time. Yeah, just let me know what time that works best for you. The only off-limit time for me on Tuesday is 3 to 4:30. Yes, just let me know what works for you in an email and I'll make sure I'm ready. So what she's got to do and what she has done is you basically spend about 2, 3, 4, 5 years researching a topic. You then have to write up that topic, write about it, all your data, analyze it, and make an argument about some new thing in the field. You have to discover something new, have done something new, do it in a new way. And then you have to basically go out in front of the public and defend it. You need to say, here is new science. Here's the way it's been done. Here's the evidence. Here's the way I did everything. And people can ask you questions. So she has to defend that to the public. And then behind closed doors, she has to defend it to her committee. And she's going to basically argue to her committee that this is new and important, and therefore she should be conferred a PhD degree. If they disagree, they won't give her one. If they do agree, she'll get one. All PhDs here at the university must have a public defense. So we're a public university. We believe in sharing, the results of our science. So every single PhD that goes through this program has to defend it. There is, I don't know where it is. I imagine if you just said like PhD defenses UMich, you'd probably find it on the internet as quickly as I would. There probably is, I just don't know where. Probably on Rackham somewhere. Yeah, no problem. And they're great to sit in on. Lots of free food, I should have mentioned that. All right. We got about 1 minute before we come back together, so, make sure you're doing your thing.
One team left to sign up.
If you have not yet signed up, you're probably going to want to do that. All right, we're going to come back together now. Some of you that are still doing your little group things, kind of do it quietly off to the side. For the rest of us, oh goodness, where did all these sheets go? For the rest of us, what I want you to do now is make sure you've got in front of you a sheet of paper that says On Playing God. You're going to want to put your name on top of that. And what I would like to talk about in biomedical engineering is a thing we have to deal with that few others do. And that's on the notion of playing God. As you can see, it actually is something of a trope. In headlines after headline after headline, biomedical engineers get accused of playing God. In fact, there's a little movie with David Duchovny. And usually accompanying this this charge of us playing God is something very close to the things we've been talking about. Synthetic biology, genetic engineering, gene editing, DNA sequencing. All these things are things that people talk about or causes us to start talking about biomedical engineers playing God. So what I would like you to do, for the next actually let's call it about 5 minutes. This is going to be one of those quiet things. I want you to answer the following questions. They don't need to be in complete sentences. Get some thoughts down, some key words, a thing here or there. What I really want you to do is have something to discuss, because as soon as you write something down, you're going to turn to people and we're going to discuss it. The things I want you to think about. When we talk about on playing God, what does it mean to you for us to play God? Are there boundaries that we ought to respect that are intimated, that are hinted at, by those who suggest biomedical engineers play God? And if so, what are those boundaries? What are the boundaries we should respect? And if not, or perhaps even if so, by what standards should biomedical engineers hold themselves accountable? Go ahead and take about 5 minutes to write something down on this piece of paper. I'm going to be collecting it at the end of the or I'll be collecting it at the end of this class. It will count for something, so make sure you write something down on it. Ah, some people thought they could get away with it.
Didn't know I had.
Anyone else need one, two? Thank you. Take about another minute to write stuff if you feel you still got some things to write down. Again, they don't have to be complete sentences. Just more ideas, keywords. After that minute is done, turn to someone near you, hopefully someone you haven't talked to before, potentially someone in another row, and discuss. Just discuss these questions and these issues. And now I'll actually force you to talk to one another. So go ahead and, just if you have a sentence, finish that one off, polish it off. But seriously, turn to someone you probably haven't talked to and do it in about groups of 3 or 4. Don't just subject yourself to one-on-one conversations. And be sure to write down their name. And if they mention anything new to you, write that down too. And you two can talk to one another. As can you two. Or you can jump to the other side of the room. Go ahead and change your. How many kids do you call?
Maybe even not.
I don't know the standard thing says like.
I think everything changes over time. It's not like that's a bad thing. Some cases it is. But I would have anything and everything. It is better. Because everything is everything seems to be taken like nothing is going in anymore. So it doesn't make sense
I'll give you about another minute to kind of wrap up your conversations, and then I'll start calling on you, especially, yeah, I'm calling you to go. I've lost you.
He made us deliberate and become and do things in our own way.
All right, I can kind of hear the group kind of decaying away. If you've got a couple of sentences, don't let me, cut you off. But I'd now like to turn this over to you. So this will actually be a convenient way of doing it. I'm going to pick on my 3 Ryans starting. So, Ryan, what's a thought you had on any of this, on this sort of playing God thing? And what's something that someone in your group had? What's a thought that was different or enlightening to you?
All right, well,
And give credit to the person who gave you the idea.
Okay, so Rohit right here said that we should draw the line at, or we should make a boundary for genetic engineering that doesn't involve getting rid of diseases to like purposely heal, just so like genetic engineering didn't change eye color or something. Or you'd have to draw the line somewhere in there.
And it should be what eye color, just so I can have these baby blues and no one else can. All right, and what are some of your thoughts on the matter?
Yeah, I agree too, and I think it's hard to draw the line because, like, say you want to get rid of genes that cause autism, but some of the best people, smartest people are autistic, so it's hard to.
That's a great point. Yeah, where do you, the difference between disability, enhancement, cure, that's a great boundary. Ryan, actually both my Ryans are right here. One can go first.
So, on like specifically framing what playing God means, the way I put it is that you're stepping into what people describe to God as God's domain. So, like, what God decides or does, rather than what people should do. And then what I thought of this, and I specifically took the case of genetic engineering, is that this argument deals with a non-unique action. We've been working on getting favorable phenotypes in like animals by breeding for millennia. Like this behavior, while more accurate and precise, is no different qualitatively than what's been done long in the past. So if we want to really like critique this in a playing God sense, we have to really analyze it in its fullest scope, and I think that's not being done. And like I'd say that it's not a bad thing, like just in the broadest sense, but more specific arguments can go from there. And then Jesse brought up a different frame to look at it. We're making like in-depth decisions for someone else, like in the sense that God would decide, who lives, who dies, stuff like that. So that's something that I hadn't considered in the original analysis. And then on setting boundaries for me, I specifically consider genetic engineering. I, for the most part, agree, but with one caveat that I've been pondering for a little while now, where like with the autism example, how do you really decide what's good and bad? And don't we do that all the time, like as parents? Like we like set up, you know, the baby's rooms because we assume that, you know, in this manner the baby will like it. We assume that the future person has preferences, and we in fact have to in order to, you know, create an environment for them. So this is a behavior we engage in already. So how different is it to say that this person would prefer this characteristic than another? So I'm up in the air about that, but that's just something to consider.
Great point. Final, Ryan?
To me, playing God is very much so about the intent of creating new organisms, types of life. Whereas I feel most of biomedical engineering currently is more about modifying what we already have. So for me, it's kind of difficult to see where exactly we're drawing the line in the sand. I think it comes down to mainly the intent of why we're doing so. It's a kind of thing. If we're going out to cure a disease, it's much different than trying to create a brand new disease just to push the boundaries of science. And Nikhil, right next to me, his view on playing God is, I found kind of interesting. It's like anything that nature can do on its own is fine. Like mutating genes, we do that naturally, that's fine. Anything that nature cannot do on its own is playing God.
So when we create plastic, we are playing God. That's great. Great points. Anyone want to add anything else to this conversation? I just sort of wanted to get your minds going about something that only biomedical engineers as engineering brethren seem to have to deal with. Yeah.
Something that I've kind of talked about is like, if we are sort of like the product of God, isn't anything we can do as humans what God is allowing us to do? And so how could we as humans play God if God is life in and of itself, I guess? I don't know.
Got sort of a Spinozian way of thinking about things. Very good. We got one up here.
Okay, so I think the very first thing I thought about is just kind of like our definition of God.
That would probably help.
In which, in this case, we're saying is the center of the universe, right? Or the thing, or something.
You're saying it.
I guess something or someone in which things or others kind of revolve around, you know. So I would say that's the definition I'm going to play with as God to kind of answer this question. And so the way I thought about it is that, let's take, for example, gene editing, right? If we use it in a way to benefit us, I think that's okay. I really think it's, I forget who was mentioning it, but it's something already kind of like naturally occurring, and anything like that that's already natural, that we use and we play around with. I think we kind of have that as our domain. We're allowed to play around with those things. I mean, it's at our disposal. We can use it to our benefit. But when it becomes God, would be when it actually becomes central to our lives, I would say, or central to our societies or the way we live.
Okay.
I guess the one thing it just kind of reminded me of was Gattaca, where, you know, we take something which is beneficial, something good, like gene editing for, I don't know, making someone, what's the right word? I guess like curing them from some kind of disease or something like that. I mean, that's a good thing. But when all of a sudden, just because someone else has a disability is less important than someone who doesn't because of gene editing, that's when that kind of technique becomes God. And I see that that's where we should hold ourselves accountable, is making sure that, you know, we're taking this good thing, but we're not making it bad by making it the center of our universe.
Well, all right. I imagine there are many other theological implications that we can all get to. We've got just a little bit more of class that I'm going to teach us. And I'm also going to try a little trick. So I'm going to pass these cards around. What I want you to do, the instructions are simple. Pick a card, any card, don't look at it. Don't look at the face of that card at all. Put it face down, don't look at it. Let's see who how we do. And hopefully I've put the fear of God in you about this. But just pass the cards back. Now we'll see. And while those are going around, I kind of want to, I'll read you one little quote. We're just going to keep going through this commencement speech by David Foster Wallace, except thinking this way tends to be so easy and automatic that it doesn't have to be a choice. It is my natural default setting. It's the automatic way I experience the boring, frustrating, crowded parts of adult life when I'm operating on the automatic, unconscious belief that I am the center of the world, as Alan suggests, is reserved for another fellow, and that my immediate needs and feelings are what should determine the world's priorities. In that regard, how are those cards going? Make sure they're going back at a quick pace, because we're about to talk about something. Namely, take one card, just a card, any card you want.
So there's a red deck in the
Oh, I suppose I should have taken a card. All right, I'll bounce back. Hopefully those are going back. Yeah, keep going. You can split the deck up, you know? You can make it go back faster. Because we're about to talk about religion. But the way we're going to talk about it is a little bit different. We have ourselves a faith, a vision. And when we talk about vision, we're talking about something pretty specific. Literally the way we see things. And in vision, there's a few things to keep in mind. We have 125 million photoreceptors. That's a lot of photoreceptors. I believe that's per eye. And of those photoreceptors, there are two types. There are rods and there are cones. Rods are the sort of light dark pixels. They only have one color associated with them. And cones detect color. Has anyone ever wondered why you cannot see colors at night, in the dark? When you stumble around your room at night, what color is your room? It's not a color. So when people start asking, at some point, you have all asked yourselves, what is color? And do I see these colors the same way as everyone else? You've no doubt thought about these things. You already know the answer. Every time you are looking at the world at night, you are seeing it in a different color. So what I want you to do now, does everyone have a card? Anyone doesn't have a card? Who's got an extra? All right, well, we're going to all try to do. Thank you very much. This isn't that much of a magic trick, so I apologize to those that are getting pretty excited. What we're about to do is we're going to take the card that we have, we're going to hold it the face will be facing us, but I want you to have it just right at the edge of your peripheral vision, the total edge of your peripheral vision, and you're going to slowly move it towards the center of your vision, and keep your eyes as straight as can be, as straight as you possibly can, and tell me, or just tell yourselves, and you can do this a number of different times, when do you see the colors and the suits? And try not to take a peek, Just, try to get a sense of when you start to see the colors. You don't have to do it all in one thing, but start to figure out your visual field. Yeah, anyone? Let's see. That's a good one. All right, has everyone done that? Everyone done that a time or two? How close does it have to be? Sort of in degrees. Yeah. We got a 5. What else we got? We got a 10, 15. Does it have to be? Can you detect the suit before you detect the value? Or can you detect the value before you detect the suit? Do they come at the same time? Color, value, suit. Isn't suit the color? Oh, gotcha, like spades. Gotcha, all right. Color, value, suit, okay. Oh, anyone different from that color, value, suit? Yeah. Value, color, suit. Okay, so you can see. And can anyone see that at the complete periphery of your vision? 90 degrees. Can anyone see that? You can see it? No. How about 45 degrees, right around here? Can anyone, staring straight ahead, can you see what the color, what that card is? So you can see, I can't really even tell I have a color there. How about right about here, about 10 degrees, 5 degrees? I can start to see that I've got black, and that's about it. It's not till about right here that I can see I've got, the 4 of clubs. All of this is a bit of a magic trick. You are operating on faith. One of the things I want to talk about is color. So how are we able to detect color? Sort of store all that in the back of your head. Color can actually be thought of in a number of different ways. This comic is from XKCD. You can look it up.
I remember this one.
It's a pretty good one. We are on our ways of thinking about color from grade school until the very future. We're right about here, which is the mix of an infinite number of wavelengths via 3 colors. We have in the center of our vision cones. Cones only account for about 5% of our total photoreceptor, or 5% of the surface area that we can see, which is why we can only see colors once they're pretty much in the center of our vision. We really can't tell color in our peripheral vision, even though your brain is tricking you into thinking you can. So you've got 3 different kinds of cones. These 3 cones have 3 different colors. They're typically called red, green, blue. I don't like to call it that. Many people are moving away from that. We now kind of think of it as long wavelength, medium wavelength, and short wavelength receptors. Because the peak sensitivity of these are at about 560 nanometers, 530 nanometers, and 430 nanometers respectively. And actually, these are those wavelengths, barring whatever the projector is doing to them. These are the colors that actually excite your peak. That should be a little more blue than it is. It's kind of purple the way it is. And this gives us what's called a trichromic vision of the world, a representation of the world through 3 colors. Does anyone know why we would have these colors? And assume that's a little more blue than it showed up. Why would we have kind of a yellow-green, a green, and a blue? Yeah.
Because kind of green and blue are really heavily prominent in the world. You've got blue sky and water, and then you've got green all the sort of plants and stuff that's kind of around. So it's early on, when evolution was really early, it's you kind of need to distinguish what's land and sea and what's in the air and what's on the ground.
That's exactly right. Color for human beings is just a way of interpreting a coding system from nature. So all color are basically the things you want to be able to determine about certain surfaces and aspects of what's going on in the environment around you. So to our ancestors in sub-Saharan Africa, knowing blue, green, and yellowish green, are really important. Knowing the earth from the ground, from the sky, really important. So color is just a coding system that was selected for by evolution in a subset of species. Not all species can see the colors that we can see. Dogs, fish. In fact, most mammals don't have trichromacy. And color sensing itself has been developed, redeveloped, lost, refound over and over and over again in evolution. Our color vision is not the only kind of color vision, nor is it the only time it's evolved. Human beings use their trichromacy. Again, that's the ability to use 3 colors to represent the full gamut of colors in 3 different ways. The first, I'll give you a little time to catch your breath, is metameric color matching. And this is a fancy pants way of saying any color can be represented by matching, or any color can be matched by mixing red, green, and blue lights of varying intensities. So in fact, all the colors that are represented on this screen come from pixels being illuminated in that projector that are just red, green, and blue. Your computer screen is just red, green, and blue. Your TV, red, green, and blue. Your phone, red, green, and blue. All those things can be combined. So the pigments in our photoreceptors also allow us, through a thing known as metameric color matching, to see a full spectrum of colors beyond red, green, and blue by varying the intensities. Yes?
Why, if any color can be matched by mixing red, green, and blue, then
why do they have these, like, why did they develop the new TV thing that also has, like, yellow and stuff to make it more, like, I can't remember, like, the color vivid or something?
I actually don't have a good answer for that. Does anyone have a good answer for that? Yeah, it's more than likely it's a marketing ploy. But yeah, I actually don't know. I suspect it would probably have something to do with more like a luster or illumination, because even though we're talking about colors, there's more to seeing a color than merely its wavelength representation, right? We can tell if a surface is dull or there's a gradient to it in the brightness. You know, this white, you know, we call it white, but this isn't white. You know, it's not the white of that paper. They're different wavelengths, but they're all kind of similar. I imagine that yellow has something to do with it, but I honestly don't know. I'm sorry. Okay, so the second way we can do it is through a thing known as opponent processing. So opponent processing is colors actually occur in opponent pairs. So for each color receptor that we have an antagonistic one right next to it. And so that's sort of what happens when you get that blue afterglow of looking, you know, up at something yellow or, you know, red and green. These antagonistic colors actually are meant to inhibit one another and antagonize one another. So this is known as opponent processing. And then finally, the most recently discovered, it was actually discovered by one of the people at Polaroid. I forget the who exactly, but it's known as Retinex. And that's actually local color experience is determined from global calculations of a visual scene. So you see all of this, and you represent the color sort of locally based on the global calculations that you're making. You're basically assuming the white down here is the same as the white up there, even though it might not be. You know, the wavelengths might be different. Your visual processing centers are doing something known as Retinex to make sure that it all looks the same. Yes?
Is that why when you have like those like magic stuff where it's
like a checkerboard in a shadow?
Yeah, exactly.
That is exactly right. Oops, I can go back. He just set me up for that. Blame Greg. This is what I do. Actually, another one that you might all be familiar with, because I'm hip and with it with the kids. The white dress, white and gold versus blue and black. That's one of these things. It's just an optical illusion.
So what color is it?
It was blue and black.
I believe it was blue and black.
That was the official coloration, but they did actually, as a thing, make a white and gold variant of it, just one singular one, just to shut everyone off.
Well, good for them.
So now you can say either one would be right because they did make one variant that was white and gold.
Well, okay. What Greg was mentioning and sort of what the yellow and gold, black and blue all represents is you cannot, no matter how hard you try, convince yourself that these are the same color. These are actually the exact same color, and your brain will not let you see it. The A and the B are the same color. I'll prove that to you. Again, nothing up my sleeves, nothing up my sleeves. We're going to pop them out, and I'm not changing the color. Popping them out, moving them, moving them, over there. Oh my goodness, look at that. Same color. Just to show you that, again, no sleight of hand, no nothing. Same colors. This looks way darker, right? And in fact, it still looks way darker. I am not making anything darker. Do you think I would spend the time? All I have to do, there are many ways you can see and prove this to yourself. But yeah, those are the same colors. Your brain is so convinced that they're different colors, you think that I would lie to you. I wouldn't. You've got to have yourself a little bit of faith, because in this world, you've got to rely somewhat on the idea that the world stays there when you're not paying attention. Has anyone ever noticed that you don't notice when you blink? You've blinked maybe 1,000 times, 100 times in this class. You probably didn't see that as a difference. Your world gets stitched together by your visual processing centers. So the reason for that is the optic nerve. Actually, we're going to blow through this. So really, strap in, everyone. The optic nerve is a bottleneck of image processing, and it does this in two ways only. The first one, if you've noticed, it's very limited in its detailed information. That all occurs right here in the center of your visual field. That's why you couldn't see the suit of the card, the color of the card, the value of the card, until it was smack dab in front of you. What your eyes are doing is a lot of your visual field is pretending it's, it's kind of filling in and it's giving you less than detailed information. So it gives you a ton of detailed information right in the center. And then what it does is it moves your eyes all around. Your eyes are darting constantly. Right now they're following me, they're jittering around at your phones, they're writing down notes, and they can do this in 5 distinct ways. This is what I mean by strap in. First way, saccade. This is just a quick motion of your eyes. Saccade, saccade, heard it both ways. Cicada is a different thing. Actually, cicadas have a mating pattern of 13 and 17 years. It's pretty cool, right? Okay. Those are prime numbers, and that's why it was selected for by evolution. It's very cool. Second one, smooth tracking, or smooth pursuit, rather. This is the tracking of moving objects. So when you're in a car and you watch another car go by as your eyes track them, or as they're following me as I sort of prance around stage, that's smooth pursuit. In conjunction with smooth pursuit is a thing known as optokinetic nystagmus. This is basically saccade with moving pursuit. So your eyes are kind of jittering back and forth as they smoothly pursue something. So your eyes don't go completely smoothly in one direction. And in fact, another thing that'll happen is known as vestibulo ocular reflex. This is when, as you move your heads, the way you can keep your eyes in one direction. Your eyes can compensate for that. It's known as vestibulo ocular reflex. And finally, the 5th kind is vergence. And this is the introversion and extroversion, basically the crossing of your eyes or the walling of your eyes, to see objects at varying depths. I will include all of this as I see. I basically want to get through 2 more quotes. There's a bunch of other stuff I wanted to say. All right, we're gonna. All right, I'm just gonna. Okay, I have come gradually to understand that the liberal arts cliche about teaching you how to think is actually shorthand for a much deeper, more serious idea. Learning how to think really means learning how to exercise control over how and what you think. It means being conscious and aware enough to choose what you pay attention to and to choose how you construct meaning from experience. And I submit this is the real, no bullshit value of your education is supposed to be about. How to keep going through your comfortable, prosperous, respectable adult life, dead, unconscious, a slave to your head, and your natural default setting of being uniquely, completely, imperially alone, day in and day out. We're going to skip through the whole on morality subject. And this is one final thing. This is if I convey nothing else to you today. I know this stuff probably doesn't sound fun and breezy and grandly inspirational. What it is, as far as I can see, is the capital T truth, with a whole lot of rhetorical niceties stripped away. But please don't just dismiss this as some finger-wagging Dr. Laura's sermon. None of this stuff is really about morality or religion or dogma or big fancy questions of life after death. The capital T truth is about life before death. It is about the real value of a real education, which has almost nothing to do with knowledge, which is why I didn't feel too bad about skipping through those final 5 points, and everything to do with simple awareness. Awareness of what is so real and essential, so hidden in plain sight all around us all the time that we have to keep reminding ourselves over and over. This is water. This is water. And next time, we're going to be talking about race, women, and sex. So please, come back. Yes, and for these, you can keep the cards, I don't really care. But just make sure you turn in the sheet that I gave you. Yes.